Okay, our next lesson as we're learning about derivatives will be how to take the derivative of two functions that are multiplied together. Another word for multiplication is the product. And if you take a look at the top of the notes here, we're going to take d dx, the derivative of f of x times g of x. Look what I've handwritten all the way up at the top. A lot of textbooks, in fact most of them, will write that out in an altered form with u and v are your two functions instead of f and g, and the prime there would indicate a derivative. What you're going to see is we'll take u prime times v, the derivative of the first, times the second function, plus u times v prime, the first function times the derivative of the second. Writing it out in this regard, with f and g, it's pretty much exactly the same setup. It's f prime times g of x plus f of x times g prime of x. Well, what I'd like for us to do very quickly is to take a look at example 1. Example 1, we have y equals x to the 2/3. So how about we say u is x to the 2/3. U prime, the derivative of that, using our power rule, 2/3 times x to the negative 1/3. Take a look at v. We'd have v is equal to x to the 4th minus x plus 2. And we'd say v prime would be 4x to the 3rd minus 1. Well, if we're going to take our derivative here, we're going to use uv prime plus u prime v. Or notice how I've changed the order here. Order really doesn't matter as long as you're going to have the first function times the derivative of the second added to the derivative of the first times the second function. Addition is commutative, so you can change the order around. What will this look like as our final answer? Well, we'd have x to the 2/3 times 4x to the 3rd minus 1 plus, here we'd have 2/3 x to the negative 1/3 times x to the 4th minus x plus 2. And what we can do right now is just combine our like terms, distribute. Remember the multiplication rule. If I gave you x to the m times x to the n, that's x to the m plus n. And if I have a power of 3, that's really 9/3. 9/3 plus 2/3 would be 11/3. So this is 4x to the 11/3 minus x to the 2/3. Similarly, we can distribute all the way over here as well. We'd have a 2/3, but 4 we can think of as 12/3. 12/3 plus negative 1/3 would be an 11/3. Here we get another 2/3, but our 1 now would be 3/3. We would get 3/3 plus negative 1/3 would be a 2/3. And then finally, distributing 2/3 times 2, we'd get 4/3, and we'd have x to the negative 1/3 power. Well, you're going to notice that we do have some like terms that we can still put together. 4 is 12/3. 12/3 plus 2/3 is 14/3. So that's 14/3, 11/3. Minus a 1, x to the 2/3, well that's 3/3. 3/3 minus 2/3 would be a minus 5/3. So that's minus 5/3 x to the 2/3. And then we do have one last expression here, one last term, 4/3 x to the negative 1/3 power. So this is the product rule. A nice way to take some derivatives. What about a quotient rule? Quotient rule helps us if we need to divide. And you have a function u divided by a function v. Here's a little saying to help you remember this. Low d high, derivative of the high, minus high d low, all over low squared. Low d high minus high d low, all over low squared. Well, real quickly, let's define our high. That's x squared minus 1. So u prime would be very simply a 2x. How about our v? Well, v is x squared plus 1. And v prime would just be plain and simply a 2x. Well, going ahead with this quotient rule, sometimes you're going to notice that it's not so easy to work out a derivative, and the quotient rule is going to help us in this regard. We'll take our low, which is x squared plus 1, times u prime, which is going to be a 2x, minus a u, which is x squared minus 1, times v prime, which is another 2x, and then down below we have the low squared, x squared plus 1 quantity squared. Certainly we could distribute a 2x everywhere, and that's fine. However, let me show you a neat little way to do this problem. We could involve factoring and say, wow, I've got a 2x there. I'm going to pull a 2x out from both of these. And it might just help us out considerably. I think you can see how that's a pretty cool step. Look, inside then, if I were to distribute that negative, I will still have my x squared plus 1, but then I'll have negative x squared and a plus 1. You can see where we're going with this. Almost done. Our x squareds will cancel. 1 plus 1 is actually going to get us a 2. So we have 2x times a 2 all over x squared plus 1 quantity squared. This becomes 4x all over x squared plus 1 quantity squared. That's our tangent line slope of the original function. Okay. Well, you can see sometimes our derivatives might get to be a little bit more tricky. And in all truth, this is where it can get to be a little more thought-provoking. Remember, we're going to need our low and our high, so let's take u is equal to 3x minus 1. High derivative, u prime, is just a 3. Take a look at v. V, our low, is 2x to the 1/3 plus 1. V prime becomes 2/3. This is x to the negative 2/3. Maybe you can see the problem that we're going to be facing in just a moment. We're going to be dealing with complex fractions, and I think you can see that pretty quickly. How do we take this derivative? Well, like we said, it's low d high minus high d low all over low squared. And let's go ahead and start substituting these things in. Our v is 2x to the 1/3 plus 1. U prime is simply a 3. Our u is 3x minus 1. But here's the part that kids probably aren't going to be too pleased to see. I'm going to have v prime is 2 over 3 x to the 2/3. Generally, we don't like seeing that. And then down below, we'll have 2x to the 1/3, or low squared, 2x to the 1/3 plus 1 quantity squared. Well, just going back on how to work with these pesky little complex fractions, I'm going to multiply this fraction by the least common denominator of what's causing the issue, and that's a 3x to the 2/3. And I'm going to do some distributing up on top. Let's see what happens. We've got a 3, we've got another 3. 3 times 3 is 9. I'm going to say this is 9, x to the 2/3. And then in here we'd have x to the 1/3 plus 1. So I multiplied my 3's together, just put the x to the 2/3 out in front. When you're multiplying through on the second case, that's the good thing. That's where your fraction completely is eliminated. Once again, tell you what, I'm going to bring the 2 out in front, and maybe that's going to look a little bit nicer. Hopefully you can see it is looking considerably better even right now. Let's do a little distributing. We no longer have complex fractions. So as I distribute here, 9 times 2 is 18. X to the 2/3 times x to the 1/3. Add those powers together. Happily, we just get x to the 3/3, which is an x. Then I take 9x to the 2/3 times 1. We'll get 9x to the 2/3. Then I'm going to distribute -2 to both. We get -6x plus 2. And forgive me, you know what I forgot to write down below? Let me fix that up. We multiplied 3x to the 2/3 in the denominator as well. That's not going to go away. That's certainly not going to vanish. So let's do a little cleaning up here. You can see that we've got some like terms of our 18x and our -6x. That's just going to combine to a 12x plus 9x to the 2/3 plus 2. Down below we have our 3x to the 2/3 times 2x to the 1/3 plus 1. And that's going to be our final answer. Okay. Well, I'm going to pause here because we're going to pick up with example 4 in the second part of the video.